The topic for our QEP project is based off of nuclear radiation, involving the subtopics natural radioactivity, nuclear equations, and radiation measurements. Most naturally occurring isotopes of elements have a stable nuclei. An atom has a stable nucleus when the forces of attraction and repulsion between the protons and neutrons are balanced. On the other hand, a classified unstable atom has a nucleus with too many or too few protons compared to the number of neutrons, which means the forces behind the protons and neutrons are unbalanced. An unstable nucleus is classified as radioactive, which means that it spontaneously emits small particles of energy called radiation to become more stable. Radiation takes the form of three different types of particles, which are alpha particles, which has the highest mass of the three, beta particles, which has the higher energy electron of the three, and gamma rays, which have high energy radiation but contain no mass and no charge. As stated before, in order for the nucleus to become more stable, it must emit radiation to balance out the protons and electrons it contains. In order to do so, the nucleus must go through the process of radioactive decay, which is when a nucleus spontaneously breaks down by emitting radiation. So like we discussed, radiation has three different types of particles, and each of these particles are represented by a symbol based on the type of characteristics they have. So for the alpha particle, it's directly related to the element helium, which contains 2 protons and 2 electrons, which gives it a mass number of 4. So right now it's represented, the mass number is on top, the atomic number of 2 is on the bottom, and He is just the symbol for helium. So for the beta particle, it has a negative 1 charge and a mass number of 0. So therefore, they put the mass number of 0 on top and the negative charge, negative 1 on the bottom, would be emitted from this symbol. Gamma rays have no mass or no charge, so both of that is represented in its symbol of 0 over 0, and the symbol for gamma is represented right beside it. Okay, radioactive decay contains a number of nuclear equations in order to help us decide and help us through the process of knowing what we need to emit in order to stabilize the nucleus. So I'm going to do an example based off of emitting the alpha particle, and we're going to write an equation for alpha decay. So the first step we need to take in writing the equation is write down the incomplete nuclear equation. So here it is, I already have it written up here. Okay, and the second step is we determine the missing mass number. In order to do so, we have to take the mass number of americium, and we also take the mass number of the emitted alpha particle. So we take 4, which is the mass number of the alpha particle from the mass number of americium. So we do this by subtracting 241, which is the mass number of americium, and we take 4, which is the mass number of the alpha particle. And then this will give us the sum of the new mass number for the new nucleus, which is going to be 237. 237 is our new mass number for the new nucleus. So let's just write that there. Okay, and our next step, we have to determine the new atomic number. In order to do so, we take the atomic number from americium, and we also take the atomic number from the particle emitted, which is 2. So we take 2 from the alpha particle, which is emitted, and then we take that from 95, which is the atomic number of americium. So we take 95 minus 2, which gives us 93, which is the new atomic number of the new nucleus. Okay, so our next step is we determine the symbol of the new nucleus. And how we do this is we take our new atomic number and match it up in the periodic table. So whichever element has the atomic number 93, that is the new element that will be on our new nucleus. So the atomic number 93 represents the element neptunium. So we write the mass number, which is 237, over 93, and we write our new element, Neptunium. So that's what we get from all of this. So the next step in completing this process is we complete the nuclear equation. So we take our information here, we take the mass and the atomic number of americium, and we write the equation of our new nucleus plus the equation of our alpha particle that was emitted, which is 4/2 He. And that is how you write an equation for alpha decay.
And now for section 9.3, radiation measurements. You start with QEP, which is the original unit of activity, and it's the number in 1 second for 1 gram of radium, and the SI unit of radiation is Becquerel. Next, we have radiation absorbed dose, abbreviated RAD, which is the unit that measures the amount of radiation absorbed in a gram of material, and its SI unit is gray. Next, we have radiation equivalent in humans, which can be abbreviated REM, which is used to measure the biological effects of different kinds of radiation. And last, we have the equivalent dose, which is used to determine the absorbed dose and is multiplied by a factor that adjusts for biological damage caused by a particular form of radiation, and its SI unit is Servet.